Today we want to keep looking at integration. We want to think about integration as multiplication, but one of the factors is continuously variable. We started off by looking at area is equal to length times width. We made the length variable, so we had to integrate the length over the width. Then we looked at a super different application where distance is equal to rate times time. The rate was variable over the time, so we integrated the rate over the time. It wasn't very different at all. Because if we just plot time on the horizontal and rate on the vertical, we're just calculating area. That's why area is the only one we really need. But then we did some problems where mass was density multiplied by area. What made this one different is that we were able to break area up into two factors. So we were calculating mass as density times length times width. That way we can make two of them variable. Also, by having one of those be area, one of the factors be area, length times width, we could make the area, the length and the width, both delta variables. That's what we did yesterday when we built a double integral, even though double integrals aren't our thing right now. But the thinking was always the same. We have some continuously variable factor. We just assume that it's going to be constant for some small change in the other factors. That way we get to multiply. Our goal is to use multiply. Our goal is to go back to whatever grade you're in when you learn multiplication. I just realized I don't know how old you are when you learn how to multiply. I only ever encounter math students, for the most part, when they're out of high school and have presumably already learned how to multiply. So as far as I know, multiplication is a skill that humans come pre-programmed with. Those apps on your phone that you can't delete. All right. So we want to look at some other applications of integration, which means we have to look at some other applications of multiplication. So another one that we want to look at is volume. Is going to be area of the cross section multiplied by height. The big goal for these volume problems is not about finding the volumes of the solid. Just like with most math problems that you do in a math class, finding the answer is not the point of the problem. Understanding the process is the point of the problem. We don't want to find, we're not really interested in finding the volumes of these weird objects that we're going to start constructing. Not physically constructing them in our mind. Actually building things like 3D printing and stuff like that, that might actually be interesting. But no, we're going to do this all in our minds. We're just going to think about these things. We're going to do practical Mythbusters. Most Mythbusters episodes are essentially just a list of equations that can be solved, but that doesn't make a good TV show. So we're going to use this volume is equal to cross-sectional area multiplied by height. We should understand that the real skill that we're building here is analytic geometry. That's really what we're going after when we're doing this. Just like in your trig class, all those trig identities were less about building your trigonometry skills and way more about reinforcing your algebra skills. I think a lot of times those things don't get stated. And I'm wondering if maybe we should. So here's what we're going to do. We're going to look at a type of volume called a volume of revolution. We're going to form a solid by rotating a region about an axis. We're going to form a solid by rotating a region about an axis. And then we're going to set up an integral to find the volume of the solid. Then we're going to use our calculator to find the actual volume of the solid. And as usual, we're going to start with some familiar object where we know what the answer is supposed to be to make sure that our process works. So if I take a rectangle, so there's a region, and I rotate it about an axis. So if I take this rectangle and rotate it about an axis, we're going to create a cylinder. From the side view, it just look like a rectangle because cylinders just look like rectangles from the side. But if we switch to a 3/4 view, we're going to see that rotation coming out of the page. But here's our original rectangle. So when we take that rectangle and rotate it about an axis, we end up making a cylinder. If I cut my rectangle down to a triangle, when we rotate it, we'll get a cone. Take this triangle and we rotate it around an axis. We'll get a cone. Then all we have to do is make the region some weirdly shaped thing that's not standard. And we'll have to calculate the volume of something where we don't know formula for the volume. We do know these volumes. The volume of a cylinder is pi r squared times h, and the volume of a cone is 1/3 of the cylinder that it's cut out of. Just like the area of a rectangle is half of the area of a triangle is half of the area of the rectangle out of which it is cut. So here's going to be the game. We're going to form a solid by rotating a region about an axis. Any questions before we begin? I don't know if they make these kinds of decorations anymore out of tissue paper, but like you start off with like this kind of a half circle thing, and it's orange tissue paper, and then when you unfold it, it's like this weird mesh-looking pumpkin. And then when you're done, you just unclip the sides and you fold it back up. Those are the things we're making. All right. Oops, not the x-axis, the y-axis. So all we need to do is define a region and then pick an axis about which to rotate the region, and then find the volume of the solid. This is just a region. This stuff in here. So we just start by defining a region. The other thing that we need is an axis about which to rotate this region, and I want to pick the y-axis. When I say axis about which to rotate the region, that's just any line. So it's not just the x-axis, the y-axis, it can be any line. Let's find the volume of the solid form. By rotating this region. about the y-axis. So here's our region, and our axis of rotation going to be the y-axis. Usually when I'm setting one of these problems up for you to do, I will say, show your calculations. And I'll be specific about what I mean by show your calculations. And I will usually also say round your answer to five significant figures. When I ask for five significant figures, that means I don't need the exact values. That is me instructing you to just use your calculator. Don't find the antiderivative and plug in the endpoints with the fundamental theorem of calculus. Just use your calculating machine to get the answer, because I just want an approximation to five significant figures. Sometimes it will not make sense that I'm asking for five significant figures, because I'll give you values that have one significant figure. That's not the point. I'm not worried about making things accurate. If your answer is correct to five significant figures, you probably did things correctly. And I just want that as an indicator to me that things have gone okay. And then when I check the rest of the problem, when I look at your calculations, I kind of go a little bit quicker, because your answer was correct to five significant figures. If your answer is incorrect, if it's only because of the significant figure thing, then I don't worry. But if your answer is incorrect, that tells me I have to find something wrong with some of your problems. And I got to tell you what places I look in the show your calculations portion of events. All right. In this particular case, we can see what this shape is going to look like. It's going to be a cone, but with parabolic sides. It's going to be a circular paraboloid. So the shape is a part of a circular paraboloid. So good thing we picked this, because we all know the formula for the volume of a circular, oh wait. I don't think we have that one. Shit, I should have started with a cone. I guess I didn't want to start with it. We never have to draw the thing, but it's helpful in the beginning to see what we're dealing with. Here's how we just have to figure out how we're gonna slice this. We're calculating a volume. How do we calculate volume? Volume is cross-sectional area multiplied by height. Volume is cross-sectional area multiplied by height. So the shape that we're getting, we're going to picture as a stack of circles. Here is a typical circle in this stack of circles. That circular paraboloid is just going to be a stack of circles. The reason that we want to look at it this way is that the area of the cross section is always a circle. The size of the circle is changing, but it's always a circle. So this is important because the area of the cross section cross section always has the same shape. Not the same size, but always the same shape. Area of the cross section is always the same shape, but it's not the same size. Two ways our cross sections can vary in size and shape. We're going to hold shape constant. That way we could write pi r squared all the way up and down. So when we want to calculate volume, volume is cross-sectional area times the height. Pi r squared, always a circle, times the height. Now, we always get a circle, but that circle is always a different size. So here's what we're going to do. I'm going to draw a typical slice. Here is a typical circle viewed from the side. So we're viewing this circular paraboloid as a stack of circles. Let's go to our original parabola, our original region, and see where that circle shows up. So here is a typical slice. That typical slice is a circle, pi r squared times h. So I need to label what r is going to be. R is a radius, and so r is always measured from the axis of rotation. Just like before when we were calculating areas, we're imagining this as a stack of circles. And so the circles are getting thinner in this stack. So that means our delta variable is going to go up and down. So our typical slice the height of this typical slice is delta y. With some change vertically. So that delta y is going to be the height. Now I can't integrate r dy because r is a function of y. I need to write r in terms of y, which means on my original, I need to go back and identify where x and y are. So I pick a point. I don't pick a point. I've already picked the point. On the point where the slice meets the function, I'm going to label where x is, and I'm going to label where y is. Here's what's going to happen with these problems. You're going to get stuck on one of these problems. You're not going to know where to go next. And I'm going to look at any drawings that you made, and you will not have labeled X or Y, or if it's a circle, you won't have labeled your R. And I'll be like, oh, what's R? And you'll just say radius. Michael, no, what's R? And it won't be labeled. And I'll say, great. R delta Y, where's Y? Y is always measured from the origin up to the slice. Any questions? The number one problem, remember, we're doing less about calculus right now and more about analytic geometry. That's why the drawing is important, to help us keep things organized. Although you can't tell from my writing, it's also important to keep things neat. If you're the type of person that's like, oh, haha, my writing is so bad, I can't even read it. You've got a serious fucking problem if you can't read your own writing. You need to fix that. That is bad. One of my best friends, no one can read his writing, not even him. He can't write. Getting better at typing. But that's a serious problem. You need to fix it. It might be that there's something wired wrong in your brain. It makes it very difficult for you. I'm not going to make fun of you for that. But I am going to make fun of you if you identify that you have something that you struggle with and you don't make an effort to fix it, especially when you're in school. And one of the things that you might have to be called upon to do is communicate by writing. You know what I mean? See also, I'm so disorganized. Then fix it. As long as you're actually disorganized, like if you actually lose stuff all the time. If you walk into my office and ask me to locate an object, I'll be able to locate it for you. So although the office looks messy, it's still kind of organized. You know what I mean? Here's one of the rules. I don't know if I mentioned this before because we do a lot of typing. That's the primary way. But now I'm starting to grade some of your stuff where you write the answer and take a picture and then post it on the canvas. You get 5 seconds. I look at what you've written. If I can't read it inside of 5 seconds, it's just wrong. I don't care what it actually says. If I look at it, it's like this horrible jumble of chicken scratch. I will not bother grading it. Michael, I can't read this. 0. You still have the opportunity to fix it because that's just how I set up classes because I think it should be that way. And I'll tell you, dude, I can't fucking read this. Try typing it or fix that broken handwriting. But you get 5 seconds. If I can't tell what you're trying to write inside of 5 seconds, you failed as a communicator. And I'm not going to put any extra effort into it. There's 40 of you, there's 1 of you. At least I cut back on the number of problems. Any questions? The primary problem that the struggle that you're going to run into is not properly labeling things. You're going to want to find some system where you write down, once you decide what your formula for the volume is, you're going to want to label those things. And if your region is defined by functions like y equals x squared, Y and X have a very specific place that they go. We don't just get to decide where those things are. We're using Cartesian coordinates. X and Y always have to be measured from the origin. Does that make sense? It's a little bit different because we start doing volume problems and we're like, it's like a Wild West. Like, oh, I can put the variable wherever I want. Woohoo! We can define this as Y or the height, or maybe this is the height up here, or maybe we pick a point 10 units above the top of the region and say that's where 0 is. We can do whatever we want. But once we say Y equals X squared, X and Y are defined and they're defined this way. We don't get to mess with that. Any questions? All right. Note that I'm also not asking that much in the picture handwriting department. My handwriting, I consider to be fixed. And you look at it, it's like, oh, what, really? Like, oh, yes, I still have low standards. No worries. Make an effort. What are we talking about? Oh, yeah. So we've actually done a whole lot of work here just by writing pi r squared and h and deciding where r is and deciding that the height is the delta variable. In our stack of circles, the height is usually going to be the variable. But it's still just area times height. Now I can see that a couple of these line up right away. The radius is equal to x. See r here, that's x there, but then I look at my delta variable, I go, ah, crap, my delta variable is delta y. I can't just put in x and integrate x squared dy. I have to write r in terms of y. Fortunately, if y is equal to x squared, then x is the square root of y. So I can write r as the square root of y. So the volume of my slice is pi times the square root of y squared delta y. At this point, we have figured out what we're going to be integrating. I'm going to be integrating the function pi times y dy. That's the expression that we're going to evaluate. The other part of the decision is the set over which we're going to integrate. We got to integrate all the y values where we have a slice. The lowest slice down here starts when y is equal to 0. And the last slice happens when y is equal to 9. So our total volume, I'm going to factor out the pi. I'm also going to simplify the square root of y squared to just be y. My discrete dy, delta y becomes a continuous dy. And we plug the values y equals 0 to y equals 9. This is a real easy integral to evaluate by hand. But I said we're going to use our calculating machines. So let's just use calculating machines. So 40.5 pi. But I said round to 5 significant figures, so we'll just write 127.23. Question? All right, we're gonna play with this idea a little bit more. We're gonna imagine when we take a region and rotate it about an axis, we're gonna slice it into a bunch of circles. So we're always gonna be slicing, looking at the stack if we slice perpendicular to the axis of rotation. Now that I've pointed out, we solved this problem by slicing perpendicular to the axis of rotation. You can probably guess what's going to come after, what's going to come about the middle of next week. If one thing is perpendicular, then the next we're going to look at what happens if we slice parallel to the axis of rotation. All right, that's going to do it for today. I will see you all on, actually, I'm going to see you all on Monday. There's no meeting tomorrow. I'll see you all on Monday. Everybody have a good weekend and thanks for playing.